In this video, I'm going to show you how to test your power analysis for when you have a completed data set, and for specifically for logistic regression analysis. So when you want to test your power analysis for logistic regression and you open your GPower, the first thing you need to do is to set your test family that we can test the power analysis for logistic regression for Z-test of the family of Z-test. And here, if you go to a statistical test, you can find the option for logistic regression. So we are pretty much done for the first settings here. The final part that we need to determine is the type of power analysis. So in this video, I'm focused on the situation when you already have a data set. That means that you know the number of participants that are going to be included in the analysis. If you don't have that, if you just want to start a new process of data collection, you would go to a priori power analysis and then would determine your required statistic here. That is very similar to what I'm going to explain now for another type. Uh, but so this is not relevant to today's video. What is relevant to today's video can be either post hoc or sensitivity analysis for power analysis. That is, these two options are relevant to when you have your data set completed, you know the number of your participants. Among these two options, I wouldn't recommend post hoc because post hoc is criticized, this method is criticized by many researchers because it does not give a lot of information about power analysis. That means that you just test your significant results, and this can just tell you that whether your significant results have a good power or not, which is not informative because even if it shows you that the statistical power is not high, still it does not question your results because you still could detect significant results despite having a lower power analysis. However, sensitivity analysis is a better option because it can give you the range of sensitive power analysis that can tell you that if your effect sizes that computed for either significant or non-significant results, if they are falling within a certain range, they might not have enough statistical power, which is still not a problem, but can have some implications for your interpretation of your results. Today I'm going to explain this option, sensitivity power analysis for logistic regression. So the first thing that you can leave many of these options as it is here. You don't need to change all of them, but there are a few that we need to change before conducting the sensitivity power analysis. So the first one is the tails, like one tail or two tail of assumption testing. That usually, I mean, especially if you have a exploratory analysis, maybe two tail is more conservative to set it that way. You can leave it for now. It's just for direction of the analysis, and we need to test it for both sides. But we now can to have a sort of a range of the sensitive powers, sensitive odd ratios that we can detect. But for now, I leave it as it is. Alpha also, you can leave it as default. If it's already 0.05, so it's good to this way. But for this way, it's about the odds of your expected outcomes, like how much you think that the proportion that you predict that you get the outcomes that you are looking for. So if you put it at 0.2 is too conservative. So I'm going just to change it to 0.5 to make it something in between, not too optimistic, not too negativistic about the potential outcome and power detections that we may have in our analysis. There are some more sophisticated way to exactly determine this based on your results, but this way also is acceptable if you want just a feasible way to test your power analysis without a lot of manual calculations. So that would be an acceptable way still to put it in zero point 0.5. And power for the level of power, again, 0.95 is too harsh. It's too strict to consider 95. Usually 0.80 is an acceptable level of power. So I'm also changing this. And the last part that I need to change is the total sample size. What's the total sample size I want to uh, that I expect that is going to be included in my analysis. Just remember that this number is not necessarily the number that is represented in your data set. This number should be the final number that is going to be included in your analysis. What is the difference? For example, imagine that your data set already have 500 participants. But after data cleaning and like removing outliers or problematic response patterns, maybe it's reduced to 435. So I know that and I should include that 435 here, not the 500. That means that I'm sure that all of these 435 participants are going to be included in my analysis. So the number that is being asked here is about the number that you want to include in your actual analysis, not necessarily the number that is included in your original data set. And that also could be the same. Maybe all the participants who responded to your survey are going to be included in your analysis, then that number could be the same. So here I know that 435 participants are going to be included in my analysis for sure. So in that case, I include 435 as my number. And I'm pretty much done with everything here. I just need to calculate now. So when you calculate, you know that so one bound of your one side of your odd ratios is 0.76. So it still is soon to interpret my power analysis. So I just take a note of that I know that so 0.76 is the lower bound of my uh, odd ratios, my expected odd ratios for having a sensitive analysis. And I just change it to the other way to have the upper bound of my odd ratio, expected odd ratio as well, that I can see that is 1.31. So now I have everything to interpret the required power for my analysis. So remember that the lower bound was 0.76 and the upper bound was 1.31. So that means that this range is very important for interpretation of for your power analysis. That means that any odd ratios, because your actual analysis, if you are doing a binary logistic regression or multinomial logistic regression, you will have an odd ratio. And if your odd ratio for each effect is between 0.76, like I change it again, if between this number 0.76 and this number 1.31 is either higher than 0.76 but is still lower than 1.31. That means that maybe your statistical power is not high enough. So your statistical power is enough, you can say that is sufficient for a certain regression effect of a certain coefficient. If your power for, if your odd ratios is either higher than 1.31 or they are lower than 0.76. Because for odd ratios, the odd ratio is stronger if it's far from 1. As the closer your odd ratio to the number of 1 is, that means that your uh, 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 effect size is smaller. That means that also your statistical power based on this might be questionable. Still, that does not mean that. So what if I do my analysis and I get an odd ratio that is like, for example, 0.80, that is bit in this range, that between the range of 0.76 and the range of 1.31. So that's not a problem. If that effects, if that odd ratio is significant, it doesn't question the significance of that odd ratio, but it can show that if I had, it can actually show something about my insignificant result. It can show that if I had a larger sample size, I potentially could detect more significant results. More than what I've already got, I could potentially get more significant results in my analysis. It especially can be the case for the effect sizes. For example, you may have in your analysis an odd ratio with p-value equal to 0.10. 0.10 is very close to 0.05, that is the significant threshold. So in that case, like for that effects, I could say that when I see that effects and I interpret that with the results of G power that I got now, so I can say that maybe because the G power analysis showed that uh, my odd ratios are mostly within this range of 0.76 to 1.31. So that means that my current sample size is not large enough. And that means that if I had a larger sample size, maybe that marginal p-value that I got, maybe that also could be significant in that case. So in general, it's just giving you an insight about your statistical power and how much conservative you should be in rejecting your hypothesis. For example, if your statistical power, if your odd ratios for most of your analysis, for most of your uh, like uh, regression coefficients is between the range that you get here. That means that probably with a larger sample size, you could get more significant results. So that is just the interpretation that it has for your result. If I want to have like an APA way of reporting the results, for example, I can have a statement like that. I can say that based on a sensitivity analysis, like using GPAVE, based on a sensitivity analysis using GPAVE, with n equal to 435 and alpha equal to 0.05, and 80% of a power that is here. This study can detect an odd ratio equal to or less than 0.76 or equal to or more than 1.31. And then I can also specify that the effects closer to 1, that means that odd ratios between 0.76 and 1.32 would require larger samples to achieve comprehensive power. So that's all you need to report in your method section if you want to choose this type of power analysis for your data.